Module 9, the peripheral nervous system, the sense of hearing. Even though I discussed parts of the ear in the last section, we still haven't covered the sense of hearing. So it's time to do that now. The auditory sense depends on receiving sounds. Well, what exactly are sounds? Sounds are made up of a series of waves moving through a medium. This medium can be solid, like when you hear sounds through a door. It can be liquid, like when you hear sounds underwater when you're swimming. It can be gas, like when you hear sounds in the air. The sound waves move through a medium by making its material vibrate. So sounds require a material to move through. Now, sound waves have two qualities, their amplitude and their frequency. When we're talking about sound, amplitude has to do with loudness. The bigger waves, the louder the sound. Frequency of sound waves, or how frequently they hit your eardrum, will determine the pitch. The higher the frequency, the higher the pitch. And when we're dealing with sound, there is one more component, timbre. Timbre helps us to distinguish what or who is making the sound we're hearing. You know the timbre of one person's voice from another's will be different when they hum the song Happy Birthday to You, right? And you can also tell if that song is being played on a guitar, or a piano, or a kazoo. They all may be playing the same amplitude or loudness, and frequency or pitch, but you can differentiate who or what is making the music due to timbre. Timbre is basically due to a sound that is made that makes more than one frequency. Any pitch you hear really has more than one frequency. There may be one basic frequency that makes the pitch, but there are other frequencies made when you hum a melody or play it on a piano. So the types of frequencies produced along with the fundamental frequency, plus the loudness, help to create the timbre of a sound. Well, now we can talk about how we hear sounds. Sound waves are vibrations traveling through a medium, most often air. As those vibrations approach you, they are collected by your auricle, which behaves as a funnel. Then they move down the external auditory meatus to the tympanic membrane, or eardrum. This membrane vibrates in conjunction with the sound waves that are hitting it. So it converts air vibrations into a solid material that vibrates. Now we are at the middle ear, which is also filled with air. The malleus is one of the 3 tiny bones, or auditory ossicles, in the middle ear. It is attached to the tympanic membrane. So when the tympanic membrane vibrates, the malleus vibrates too. It's connected to the incus, and the incus is connected to the stapes, a tiny little stirrup-shaped bone. So as the malleus vibrates, the incus and stapes do as well. The tiny bones then concentrate the sound vibration onto the oval window, which is made of flexible material. These 3 bones help to increase the strength of the vibration so that the fluid on the other side of the oval window will begin to move. You see, the other side of the oval window is the location of the inner ear, and the inner ear, as you already learned, is filled with fluid. The oval window leads to the inner ear then, specifically the cochlea. Here's a close-up of the cochlea, uncoiled a bit so you can see what's going on. The spiral organ is coiled up 2.5 turns inside the coiled cochlea. The spiral organ is made of sensory receptors for sound, called hair cells. It sits on top of the basilar membrane. Well, there is one more membrane here. It is a gel-like substance called the tectorial membrane. It is located right on top of the spiral organ and touches the hair cells there. When the oval window vibrates, the fluid of the inner ear begins to vibrate. If those vibrations are of a very high frequency, which means that the sound is a high-pitched sound, a vibration will occur at the base of the basilar membrane. That means that high-frequency vibrations affect the basilar membrane near the oval window. This movement will cause vibrations to occur in the tectorial membrane. The tectorial membrane brushes up against the hair cells of the spiral organ. And when these hair cells move, then action potentials in their associated neurons will result. If the vibrations coming to the oval window are of low frequency, then the vibrations will cause the apex or far end of the basilar membrane to vibrate. This then triggers vibrations in the part of the tectorial membrane that touches the hair cells at the apex of the spiral organ. When these hair cells move, then action potentials will be triggered on the associated sensory neurons. So the ear can identify different frequencies based on where the vibrations occur on the spiral organ. If it is a higher pitch, which is a higher frequency of sound waves, the basilar membrane will vibrate closer to the oval window. Conversely, if it's a lower pitched sound, which is a lower frequency of sound waves, the basilar membrane will vibrate further from the oval window, nearer to its apex. If the associated sensory neurons nearer to the oval window are stimulated, then they will send signals to the auditory cortex of the brain that will identify the sounds as high-pitched sounds. And if associated sensory neurons nearer to the apex are stimulated, then they will send signals to the brain that will identify the sounds as low-pitched sounds. Well, what about volume? We know we can tell the difference of a loud sound versus a soft one. So how do we do that? Well, loudness is determined by the amplitude of the sound waves. The bigger the amplitude, the bigger the vibrations of the tympanic membrane are. This means it will move back and forth more strongly. Frequency refers to how many times it will vibrate back and forth, or how frequently it will vibrate. But amplitude refers to how far back and forth each motion is. Bigger amplitude of sound wave means bigger movement of the tympanic membrane, bigger the amplitude of the vibrations in the ossicles, and bigger vibrations in the cochlear fluid. And a big amplitude of vibrations will trigger a higher rate of action potential. Higher rate of action potentials is interpreted by the brain to be a louder sound. So to sum up, we can say that the location of the vibrations in the spiral organ determines the pitch, which is due to frequency. And the amplitude of the vibrations in the spiral organ determines the loudness of the sound.